Next, let us say that you are asked to decompose this rational expression into partial fractions. So x square plus 2 by x minus 1 whole square into x plus 2. So this denominator is already in the factorized form. So you don't need to separately factorize it. So now, the first step in decomposing it into partial fractions is that you need to assume the partial fractions. So here you have the denominator factors as x minus 1 whole square into x plus 2. Now, if you try to decompose into two factors, something by x minus 1 whole square, the first factor, plus something by x plus 2. If you try to decompose this into two partial fractions. So let us see whether you can do this or not. So first, if these two are equal, then on taking LCM, this expression has to be same as this. So if you take the LCM, you get x minus 1 whole square times x plus 2. So here you have a times x plus 2 plus b times x minus 1 whole square. So the denominator and denominator are same, so these two denominators gets cancelled. So the numerator has to be same as this. So x square plus 2 has to be same as. So if you expand this, you get bx square, right? You have bx square plus with x you have an a here and you have a minus 2bx, so minus 2b plus the constant term is 2a plus b. So now if these two have to be equal, each of the coefficients have to be same. So first equation is the coefficient of x square should be same as coefficient of x square, 1 is equal to b. The second equation is the coefficient of x has to be same as coefficient of x. So the coefficient of x here is 0 is equal to a minus 2b. And the third equation is that the constant term here should be same as the constant term. 2 is equal to 2a plus b. So first b is equal to 1. So if b is equal to 1, a is equal to 2. But surprisingly, 2a plus b is equal to 5, not equal to 2. That is, you cannot at the same time satisfy all the three equations. That means this expression will never be equal to this expression for any value of a and b. That means I could not split this into two partial fractions. So if I write the partial fractions in whatever way I want, it's not necessary that they'll work. You have to choose the fractions nicely. So the simple technique is that when you choose the fractions, the number of unknowns should be same as the number of equations. The number of unknowns should be same as the number of equations. So usually, as you see here, you have three equations, but you have chosen only two unknowns. So that is why you got problem here. So the simple technique that underlines this decomposition is that once you take the partial fractions and take the LCM, the number of variables that you have here should be same as the number of variables that you have here. So if you take a cubic expression here, if it has to be a proper fraction, the maximum degree that you can have in the numerator is 2. And a quadratic expression has three unknowns, that is ax square plus bx plus c. So whenever you have a cubic in the denominator, you need to have at least three fractions. Whenever you have a fourth degree, you have to have at least 4 unknowns. You have to include 4 unknowns so that you get 4 equations with 4 unknowns and you can solve them. So I hope you are understanding the crux of selecting partial fractions. So the thing that you have learned till now is that if you take the partial fractions in whatever way you want, you won't be able to solve them always. So you need a standard rule of choosing the partial fractions. That is what we are going to see now. So I'll give you the formulas, and the underlying concept is that once you take the LCM, the number of equations that you get should be same as the number of unknowns that you have. So to maintain that, the rule that I am going to say will help you.